Okay, so my name is Zdravko Siketić. I'm coming from Ruđer Bošković Institute in Zagreb. And in this presentation, I will speak about two techniques we are performing at our laboratory. It's Rutherford backscattering and elastic recall detection analysis. There will be two parts of the presentation. I will a little bit speak about simplified theory of the both techniques to understand how they work. Then I will show you a few examples. And when the presentation finished, I would ask you to ask questions in chat or in live. And when you finish with questions, we will start with the movie, which is about 20 minutes. And in this movie, we will present you actually a practical part of this. So I will start with RBS, which is Rutherford backscattering, and ERDA basics. You probably already seen this slide yesterday during the Milko's talk when he explained what ion beam analysis is, and also this morning when you heard about particle-induced X-ray emission. What this graph tells us and this picture, it's basically what happens when the ion of MEV energy hits the sample. So there are many products of interaction. Can you see my mouse moving around?
Yes, we can see it.
Yes. Okay, so I will show by my mouse. So when the MEV ion hits the sample, you can have production of the X-rays, which you heard about this morning. We are calling PIXI spectroscopy. You can have nuclear reactions. It depends on how high energy is of the primary ion beam. You can monitor transmitted particles. You can have backscattered particles. And this is actually the basics of the Rutherford backscattering. In principle, to have a backscattered particle from any ion in the atom in the sample, this particle has to be lighter in mass. So for this Rutherford backscattering, we are mostly use a light ion beam as a primary ion beam, like a proton beam or helium beam. And on the second part of the talk, you will listen about this. It's, let's say, similar to Rutherford backscattering, but in this case, you detect the atoms which are ejected from the sample. So in order to do that, we need to use heavier ion beam as the primary ion beam to eject everything what is inside in the sample. So, but first we will concentrate on this part. This is Rutherford backscattering. When you have backscattered particles scattered back from the nucleus inside of your sample. As I told you, for this we are using light particles, and this is a very short GIF which shows you what is happening when, for example, helium particle enters in the sample. And some of these particles, if they are close enough to the nuclei, they are backscattered. First of this experiment was performed now many years ago in 1909. This is a famous Rutherford experiment where he proved actually that atom is made from the solid core, where the whole mass is concentrated, and this core has brings the positive charge of the atom, and you have electrons which are orbiting this nucleus. In this picture above, you see that before Rutherford model of the atom, you had this Thomson model, where the negative, these blue dots are electrons, were plunged inside of the positive, let's say, C of the positive charge like plum pudding. That's a model of the plum pudding. And if you have a source of the alpha particles, radioactive source, all particles should pass through and none of them should be backscattered. But when the Rutherford performed the experiment, what he observed when you have an alpha particle source hitting the gold foil, some of the particles were backscattered. That was completely not explainable by this Thomson model of the atom. And Rutherford concluded that actually this could happen only if the atom consists of the solid core, where the whole mass of the atom is concentrated, and that is the only way how the particles can be backscattered. And that is actually the whole basics of the Rutherford backscattering spectrometry. So when you look how to determine the unknown mass of in your sample, it's very simple. So if you look this simple scattering sketch, this you already learned in the high school, and you can calculate what is the energy of the backscattered particle M1 if it's backscattered from the mass M2 at a certain angle theta. So if you know the masses of the incoming particle and particle in the rest and the scattering angle, you can easily calculate what is the scattering energy of this primary particle. But in Rutherford backscattering, what we are detecting the energy of the backscattered particles. So if we know that our detector is positioned at a certain angle, we know the primary ion beam energy, we know the mass of the primary ion beam, and from the measured energy of the backscattered particle, we can measure and determine unknown mass, which is inside of the sample. This is how we identify which element we have in the sample. The second question is, how much of this element is presented in the sample? And this is governed by the dynamic of the scattering. Since in most of the cases, we are working in the MeV energy range, and we try to work in the below this Coulomb threshold barrier. So what we have is pure Coulomb scattering of the primary ion beam on the atom inside of the sample. This Coulomb scattering is described by the Rutherford formula written here, and it's proportional to the square of the Z of the primary ion beam and the Z of the element inside of the sample, and it is in inverse square proportional to the energy of the primary ion beam. On this graph, you can really easily see what is the, let's say, relative yield of the backscattered particles on different from the different ions inside of your target. So as you go to the heavier element, you will get much more backscattered particles. That immediately means that this technique is more sensitive to the heavier elements than to the lighter elements. And it is usually used for the determination, it is used to quantify how much of you have of the heavier element presented in the light matrix. So this is how the setup for the RBS experiment looks like in our lab. So you have ion beam coming from the accelerator. It hits the sample here, and we have, beside X-ray detector, we also have a particle detector which detects backscattered particles. It's a simple surface barrier detector. It's a silicon detector. I will not go in the details how it works, but the charge produced inside of this detector is proportional to the energy of the detected particle, and that is the basics how we calculate the energy of the backscattered particle. Besides determination of the which element is presented in the sample and how much we have of this element inside. We can also do depth profiling using Rutherford backscattering. I didn't go into details here with the stopping of the ions in the materials, but as ion goes inside of the sample, they are losing energy, and they are also backscattered for a certain depth. I will show you later on how this looks in the spectra if you have a thick target, and how can you do the depth profiling. In this graph, we have a experimental value, an experimental spectra of the sample, which consists of the very thin gold layer on the top, then which is 8 times 10 to the 14 atoms per square centimeter. Then we have a layer of the chromium below, 10 to the 15 atoms per square centimeter, and everything is deposited on the thick silicon. For this experiment, we used 2 MeV helium beam, and the detector was placed at 140-degree angle. And how the spectra looks like, you can see on this graph. So the heaviest element in the sample is the gold. So that means that the backscattered particles of the highest energy corresponds to gold. Since the gold layer is very thin, we cannot expect nothing more than the peak in the spectra, and this is the peak of the gold. So the next peak in the spectra belongs to the chromium, which is below of the gold layer, and this peak is here. And also you see that this peak is lower than the gold peak. Even there is more chromium than gold, and this is why, because the cross section of the which goes with the Z square is much higher for backscattering helium from gold than helium from chromium. And at the end, you have this continuous spectra, which corresponds to the silicon from the substrate. This is a very simple formula which actually tells you how to do quantitative analysis. So the yield of a certain element in the peak is proportional to the, of course, total number of incident particles. It's proportional to the concentration of this element inside of the sample. It's multiplied by the cross section of the reaction and detector solid angle. Roughly, for RBS, I can tell you that it can be used also for depth profiling with depth resolution of the 5 nanometers at the surface. This depends on the geometry of the setup and the energy of the primary ion beam and the mass. Probing depth, we can probe and depth profile films the thicknesses of few microns, also depending on the primary ion type and energy. And the sensitivity also depends on the element and can be a few tenths of ppms for the heavy elements. You can see, for example, here how the gold peak is very nice, and it's only 8 to 10 to the 14 atoms per square centimeter. So the sensitivity can be in the range of 10 to the 14 atoms per square centimeters for the heaviest elements. And on this graphs, you can see what is the thickness effect on the Rutherford backscattering spectra. Now we can speak a little bit about depth profiling. So we had a film consisted of the titanium nitride at the surface. Below, it's magnesium oxide, and then we have a silicon as a substrate. No, sorry, it's titanium nitride on magnesium oxide substrate. So here on the first graph, we have 300 nanometers of titanium nitride. So now we don't have a peak as we had it before for very thin films. And this is why, because the ions, when they go inside of the sample, they are losing the energy. And also when they go out through this layer, they're also losing the energy. So this is actually the surface of the titanium. And from this other side, this is the interface between titanium and magnesium oxide. Also, this is the magnesium edge from magnesium oxide. We have a nitrogen from titanium nitride, and we have and also the oxygen. If we go to the thicker layer, like let's say 400 nanometers, you can see immediately that this is much wider in the energy. In the y-axis, this is the energy in the ADC channels. So for the thicker layer, you have also the longer energy profile. If you go to 600 nanometers, it's even bigger. So you can see that if there are some variations in the titanium concentration through the layer, we should see this here in the spectra, but it's quite smooth, so I could say that this is quite uniform layer. So this was briefly what can you do using radiofrequency backscattering, and just just remember that this technique is used for the detection of the heavy elements in the light matrix. But of course, we want to have a complete picture. We also want to have information about light elements like hydrogen or deuterium or helium. And for this, we are using elastic recoil detection analysis, or ERD. So far we were speaking about backscattered particles. Now I will speak about recoiled particles from the sample. Because when you recoil, you recoil actually everything what is inside, and you detect this with also energy detector. You can see also here that was rather for backscattering, and now we have the little bit different configuration. We have a heavier mass which hits the lighter mass, and then you recoil this mass. Also, this primary ion beam is also forward scattered by the constituents inside of the sample. Usually, since we want to look what is inside, I mean, of the thick targets, that's why we cannot have a normal geometry, but the beam is entering at some angle towards the sample surface that we can detect recoiled particles which are going out towards the detector. This is, let's say, typical ERD configuration. Kinematic in this case is a little bit different. For those who want, maybe can calculate this kinematic factors for the RBS and ERD. It's very simple calculation. It's a little bit different kinematic factor, since we are now talking about recoils. And the cross section is also a little bit different, but still it goes by square of the primary ion and also atom in the sample with square of the Z of the atom, Z number. And if you use these two things, like kinematic factor, which defines the energy of the recoils and identify the mass of the recoiled particle, and the cross section, which will help you to calculate the concentration, you can easily convert energy spectra to depth profile. We have a softwares which are doing that. Nobody does that by hand. So how the typical spectra would look like for this simple target? So I made targets made from hydrogen, carbon, and oxygen. Hydrogen are red dots, carbon are pink, and the oxygen is blue. And I use, for example, carbon beam. So carbon comes here, recoils the oxygen, recoils the hydrogen, recoils the carbon as well, but also the primary ion beam is also forward scattered by the oxygen and by the carbon. And everything is detected by energy detector. And this is actually how the spectra looks like. So there are now different colors in this spectra represents different elements. For example, green one, it's a recoiled hydrogen. So This is how the spectra of the recoiled hydrogen looks. This is a mylar film in transmission geometry for 10 MeV carbon primary ion beam. You have recoiled oxygen, as I said, but you also have a carbon scattered on oxygen and carbon scattered on carbon and recoiled carbon. So the spectra is not that simple now, because what you measure if you have only energy detection is this blue spectra here. So you really need to know something about your sample before you do the analysis. Otherwise, you can get wrong conclusions. So I will tell you now how to maybe resolve this issue of that you know something in advance about your sample. So there are two types of geometry. I already mentioned this reflective geometry, if you have a thick targets, and if you have very thin targets, so the recoils can pass through, and it can be done also in transmission geometry. Transmission geometry is only for the thin targets, but energy straggling of the primary ion beams deteriorates depth resolution. But if you work in the reflective geometry, then you need ultra flat samples, but it has excellent surface depth resolution. So the main problem is with ERD comparing to radiative backscattering is that in radiative backscattering you detect only one particle species, but in ERD you detect everything from hydrogen to everything what is presented in the sample. And if you have only one energy detector, it cannot know. For him, 2 MeV helium, which entered in the detector, or 2 MeV oxygen is the same number. So he cannot tell you, did you measure now oxygen or helium or something else. But there are ways how to go around. And the simplest way is to put a stopping foil in front of the energy detector. And this is usually used if you want to detect only hydrogen. So you adjust the thickness of the foil to stop everything except hydrogen. And hydrogen will pass through like a filter, and you will just get a hydrogen spectra. You can also separate the elements if you have a thin, it's a so-called delta E detector, and the signal from this delta E detector is proportional to the Z of the ion which passed through. So if you measure delta E and E, you can have a Z separation of your elements inside of the target. Or you can do time of flight. So you measure time of flight between 2 points. So ion of the same energy and different mass have a different velocity. So by this, you can separate ions by mass. Or there are some sophisticated magnetic spectrometers. I will not speak about them now. I just wanted to show you what we have here at Ruđer Bošković Institute. We have two types of spectrometers for ERD. One is the ion electron emission ERD system. It's quite similar to this delta EE setup, but instead of the delta E detector, we have a detector which consists of the thin carbon foil and energy detector. From this, when the ion passes through the thin carbon foil, it emits electrons, which are multiplied by microchannel plate detector. And the pulse height of the number of these electrons emitted from the foil are proportional to the Z of the ion. So you can see here, this is a pulse height from the microchannel plate. It depends on the energy of the beam and the mass of the beam. And this is how this spectrometer looks like. It is attached, in our case, to the nuclear microprobe, so we can do also the imaging of the sample, but mostly it is used to separate hydrogen from the rest of the elements inside of the sample. The second spectrometer we have, and this is the part of the CERIC instrumentation, it's time of flight ERD spectrometer. So as I said, here we measure the time of flight of the recoiled particles. Usually we use heavy ion beam like chlorine, gold, iodine, of energies of 20-30 MeV. You heat the sample and you recoil everything out. You measure time of flight between these 2 points, and you measure the energy in coincidence. In this, for our setup or setups around the world, depth resolution is close to the 1 nanometer at the surface. It goes then bad when you go deeper inside the sample. You can profile thin films thickness of few hundred nanometers. So it's not microns as in case of the RBS, because we use here heavy ion beam, and they have much higher stopping, and they stop much shallow inside of the sample than the light primary ion beam like protons. And sensitivity is like 0.1 atomic percent for the light elements. This is a picture of our time of flight ERD instrument. So this is the experimental chamber where we put the samples. This is a time of flight telescope, and this is a gas detector used for the energy detection. The very heart of the time of flight telescope is timing gate, which is used as a trigger for start and stop measuring in the time of flight. The detection and the triggering is also based on the emission of the electrons from the foil. And those electrons are then focused down to the microchannel plate detector, and that produces a signal which is used then for the start. And then at another position, like half a meter away, you have another one for stop signal of the recoiled particles. Okay, and then I'll go to the more examples. I have 2 examples with RBS and 2 with time of flight ERD. First RBS example was analysis of the textile or metal threads. And what we wanted to see, is there any intermix between the gilded layer, so it's plated with gold, and the silver, which is below it. We had 2 textiles. One is this thin, this is just a code name, and the thickness of the gold in this case was around 230 to 240 nanometers. And this is the RBS spectra. So you can see the green one is the simulation of the gold layer, and the blue one is a simulation of the silver layer. And we could only fit this spectra that we assume that there is a diffusion between the gold and the silver layer. We had the same analysis for the cloth, but with a thinner layer of the gold, about 90 nanometers. And this diffusion, so the thinner layer, you see that there is more or less look like peak of the gold. And this interdiffusion was much smaller for this thinner layer. The second one example for RBS is the characterization of the amorphous silica solar cell. So this is the composition of the solar cell. You have an aluminum contact. Below is a silicon layer, then in this tin oxide layer, and you have silicon oxide. And the question was here, how thick is aluminum and how thick is the silicon layer? So you can see that you really, if you want to extract good information, you need to choose a right primary ion beam. For example, if you use only 3 MeV protons, the spectra will look like this. You will have a thin signal, okay, but the silicon and aluminum signal are mixed. They are overlapped because they are very close in the mass, and you cannot separate them by protons by detecting the energy of the protons. That's why this is what you can see here in this graph. This is a kinematic factor. So if you want to have a better mass resolution, let's say, then you need to choose the heavier ion. And what we choose here, which we decided to use a lithium beam 5 MeV. And this how spectra looks like. It's different now. So you can see that the very thick thin layer from this delta E, we can calculate the thickness, but also we can see nicely overlapping of the silicon and aluminum layer, but they are forming this peak here. So this the thickness of these two layers can be easily extracted actually from the simulation of the spectra. And now I have two examples of time-of-flight ERD. First is the analysis of the multilayer. So it's a sample consisted of the 5 multilayers of aluminum nitride, titanium nitride, thickness of the 20 nanometers. And for this experiment, we used 25 MeV iodine beam. We used incidence angle 5 degrees towards the sample surface. If you remember, in ERD, time-of-flight ERD, we collect time-of-flight and energy in coincidence. And this is how it looks like in the map. On the y-axis, you have time-of-flight. On the x-axis, you have energy. And these, let's say I call them bananas, they belong to the certain elements. So we can identify there is hydrogen, some contamination of carbon, nitrogen, oxide contamination is on the surface. And you can see these aluminum islands, which means that this is aluminum for each of these 5 aluminum multi-layers. So there's aluminum. So now there is a gap. That means that there is a titanium layer here. Then you have aluminum again. So when we have 1, 2, 3, 4, 5 of them. When you plot aluminum events and project them, for example, on the time-of-flight axis, you can nicely see 5 of them. You can also see that closer to the surface, the layer, you have a sharper peak, which means that the depth resolution is better. Yes, you go deeper in the sample, this peak is more broad, which means that depth resolution is deteriorating. What we calculated after the analysis, that the stoichiometry of the layers, so it's 1-to-1 in each of them, and the thickness of aluminum nitride was 24 nanometers and titanium nitride was 40 nanometers. And the last example I'm showing is the analysis of the single pure film. It's around 100 nanometer, again, titanium nitride. We chose a little bit different beam this time, 20 MeV bromine, and different scattering geometry. And this is how the time-of-flight ERD map looks like. Again, we can identify the hydrogen, carbon, nitrogen, silicon, oxygen, titanium, and this is a scattered primary ion beam. And when you do the offline analysis using actually free softwares, you can really nicely have a depth profile. And this is the depth profile of titanium nitride and all elements inside. So there is an oxygen peak at the surface. The blue one is the titanium profile. The dark blue one, the light blue one is the nitrogen profile. And this purple is the silicon. And you can also see that there are some oxygen and the hydrogen elements in the interface between these films. So there was some contamination of the silicon surface during the deposition. From this plateau here, since we have atomic content, we can calculate the ratio of the titanium and nitrogen. It's actually 1-to-1. And from the integral of the depth profile, we can calculate the total number of atoms per square centimeter. So we have stoichiometry, we have atoms per square centimeter. And if you know the density, you can calculate the thickness in nanometers, which is around 100 nanometers. So by this, I reached the end of the presentation. And now I'm open for questions. You can ask in chat, or you can ask directly by connecting.
Hi, good afternoon.
Hello.
Hi, good afternoon. Actually, like in your presentation, you say that the back counts of the backscattered is proportional to the Z square.
Yes.
And when we have a look on the spectra, but the number of counts for the silicon is higher than the chromium.
Ah, wait. Okay. It's this one.
Yes, this one.
Yeah. So the problem is that if we had here, so this is a continuous spectra. So it's integral, actually, integral of many peaks like this. That's why it's higher. If we had, for example, pure chromium, then you will have a step here, and it would be much higher than the silicon step. This is just a peak, which is actually peak because of our limited energy resolution of the detector. That's why for you it appears that it's smaller.
Okay,
but
I understand. And how much time it takes for one sample to measure this RBS spectra?
Okay, it depends on the concentration of the elements, but usually we have some, let's say, normal numbers of the elements, and it could be like 15 minutes
15.
For RBS, and for ERD it takes longer because of the smaller solid angle of the detection. And
okay, thank you.
Any other question?
I have a question.
Yes.
So you say that 200 nanometers is thin film, 100 nanometers, but what about the configuration of the film? Does it have to be like homogeneous thickness, or it can be somewhere thicker or thinner?
Yeah, I understand. You mean laterally? If you have...
Yeah, yes, thickness of the film. I mean, if I have a thin film, for example, of some material, that it's not even a thickness everywhere, and
Oh no, then it's complicated. Yeah, then it's complicated. We could analyze it, but then we need to know in advance this inhomogeneity, let's say.
Mm-hmm.
Yeah, that could also happen if laterally you have some islands of the material not uniform, and then the spectra looks different. And if you don't have any information from IFM or from electron microscope, then you can draw wrong conclusions about your sample. Yeah.
No, but in principle, for example, we have IFM measurements. AFM is just a very common technique that we use, but our samples are never super smooth or even thickness. I mean, the variations in thickness are not big.
Yeah.
But you said 5 nanometers is the...
that is only for extra flat samples. Yeah.
Okay.
If you have roughness, that destroys your depth resolution, especially if you do in some how to call it, not orthogonal, but this inclined, yeah, geometry. Then yeah, that destroys the depth resolution. Yeah.
Okay, thank you.
Any question? If you still...
Hi. Just one very general question. Like if we want to use this RBS technique for our samples, so it's like through CERIC proposals or just a direct connection?
Well, you can go to the CERIC, of course, and apply for the beam time.
Okay.
Or we also do, I mean, we have many ways how to get the beam time here. We have other TA projects, but I will not advertise them now because we are in a CERIC school. But the CERIC, you can apply through the CERIC, or you can pay directly, of course, if you are a private company. But the CERIC is the easiest way for you to come here because you get paid for your trip, and yeah, so yeah.
Thank you.
But you can also visit our webpage, and you will see the options how to get the beam time in our lab.
Okay, for sure.
So after now you will see now how this RBS and ERD looks in practice, and how our laboratories looks like in instrumentation which is used for this. We filmed you will see now the movie about 20 minutes. It was filmed for the one similar school also. So I will ask now Darius or somebody else to play the movie. I will stop share my screen now. And later on, when the movie finished, if you have still some questions, I will be here and answer it. Okay, so see you in 20 minutes.
Just 1 second, and we will start the play of the video.
So please confirm if you can see my screen and hear the video.
Yes.
In a few seconds.
Yes.
Okay, perfect.
Everything is perfect.
Hi, I'm Tony. And I'm Zdravko, and we are coming from the Laboratory for Ion Beam Interactions, Ruđer Bošković Institute in Zagreb. Here in this video, we will demonstrate you 2 ion beam analytical techniques, radio for backscattering and elastic recoil detection analysis. The main idea of today's experiment is to demonstrate you and to show you how radio for backscattering, RBS, and elastic recoil detection analysis, ERD, measurement process works. Contrary to the PIXA experiment, where you saw that you can calculate the total amount of the material present inside of the target, with RBS and ERD, you can determine, beside the total concentration, also the depth distribution of the elements presented in the target. This depth profile will give you the concentration distribution of the element from the very top surface of the material up to the, if you do RBS with light primary ion beam and light matrix, up to few microns depth inside of the material. For today's experiment, here on the table, you can see we will use different kind of the samples. We need 2 types of the samples. First, we need to do energy calibration of the radio for backscattering spectra, and for this we will use thin carbon target coated with a thin gold layer, which will give us, you will see later on, 2 peaks for the energy calibration. Besides the energy calibration, we also need to calibrate solid angle of the RBS system, and for solid angle calibration, we will use implanted stardust with known concentration of the implanted material. Implanted stardust is usually produced by the implantation on the implanters in such kind of the silicon wafers, and the standard we will use today is implanted arsenic and implanted argon in the silicon wafer. Once we finish the energy calibration and the geometrical calibration of our system, we will measure the unknown samples, the thin layers of the gold deposited on the silicon oxide, thin layer of the gold deposited on the carbon, and multi-layer consisted of the indium and chromium deposited on the silicon. And our task will be to determine the total amount of the gold and total amount of the indium and chromium layers deposited on the different substrates.
For the RBS experiment that we'll be performing today, we'll be using the same accelerator as we did for PIXI. However, since the RBS technique works much better with helium ions, we need to use a different ion source. We will be using the dual plasmatron ion source. This ion source produces positive ions, which are then changed to negative ones by the charge exchange mechanism. After this mechanism, they are accelerated by the positive potential of the tandem accelerator. When the negative ions enter the stripper of the tandem accelerator, they are changed to positive ions of charge states +1 and +2. These positive ions are accelerated along the beamline towards the analyzing magnet. Using the analyzing magnet, we choose the +2 charge state. Since the terminal voltage is now at 600 kilovolts, this gives us a beam energy of 2 mega electron volts. Later, using these two magnets, this beam is focused and it enters the analyzing chamber. The samples are already mounted inside the chamber. They're mounted on a sample holder, which is a ladder that can be controlled using our data acquisition system. Here we have a collimator, which controls the shape and size of the beam. Above it is the RBS detector mounted at 15 degrees from the beam. This gives us a scattering angle of 165 degrees. Also, here we have the forward scattering detector, which can be used if we are analyzing some kind of thin film. So we will only be using one detector today, which means that we only need one electronics line. This consists of an amplifier and an analog digital converter, which is connected to the data acquisition system. When the vacuum is established, we can open the valve towards the beam line.
So on the right monitor, now you can see the beam is hitting the scintillator, and you can see this bright spot, which is caused by the emission of the light when the beam is hitting the scintillator. Now we will position our first sample at this point. First sample is thin carbon coated with the gold, and we will use this sample to make energy calibration of the RBS spectra. So now I will start to move sample holder. While we are moving, you can see here also this ring here is actually a suppressor in front of the target, and we will collect the charge from the target in order to make charge normalization. This suppressor is for the suppression of the electrons, and usually it's put it on the -400 volts. Now, after putting the bias on the silicon detector, we can start the measurement. We'll press the start, put the file name, and press start. So what you see on this left screen is the signal coming from the ADC, which is collecting the events from the silicon detector. And you can see immediately two peaks, the peak on the lower energy and peak on the higher energy. Peak on the high energy corresponds to the gold on the carbon foil, and peak on the lower energy corresponds to the carbon foil. From these two peak positions and from the energy of the incoming beam, which is 2 MeV helium, and non-kinematics, because we know that our detector is at 165 degrees, we can calculate the energy of the backscatter helium from the gold and from the carbon. And these 2 points can be used for the energy calibration of the collected spectra. We also have to monitor on the counting rate, which has to be lower than 1000 counts per second. Now it's roughly 100 counts per second, which is okay, because we want to avoid pile-up in the spectra, and also we want to avoid sample damage. In order to do that, we need the currents of the helium beam in the range between the 5 and 10 nanoamps. It depends on the sample composition and thickness. We started to collect spectra of the second sample. This sample is very important because it will be used for the calibration of the solid angle of RBS detector. It is the sample of the implanted argon and arsenic with known concentrations in the amorphous silicon. So you can see the spectra, now it's on logarithmic scale because the concentration of the implanted elements is very low. So the first peak belongs to the arsenic implanted. The second peak belongs to the argon, which is implanted in silicon. And this continuous spectra here belongs to the silicon wafer. If we move to the linear scale, you can see bump. And this bump actually corresponds to the amorphized silicon. So all these two elements are implanted in an amorphized silicon in order to avoid the channeling in RBS spectra, which is clearly seen here because the signal of the silicon below the amorphized layer is lower than it should be as it is in the amorphized region. So for the precise analysis, we need just to use this part here. When we go back to the logarithmic scale, you can see that arsenic and argon peaks are sitting on this linear background, which is coming actually from the pile-up from the silicon signals, and this has to be subtracted during the analysis. Now we positioned our sample holder to the third sample, which is a sample of the unknown concentration, but known composition. It's gold evaporated on the silicon dioxide. Now we will start the measurement. I will put the spectra number and start with measurement. Immediately in this spectra, you can see that there is a peak, which by kinematics corresponds to the gold. And its peak, that means that the layer is very thin. And the second part of the spectra belongs to the helium scattered from the silicon dioxide. This first edge corresponds to the silicon edge, helium scattered from the silicon and coming from the depth of the silicon. And on this spectra is superimposed helium scattered from the oxygen. And here you can see the oxygen edge. Immediately you can see the difference between the thin sample and thick sample. Thin sample gives you only peaks in the RBS spectra, and thick sample gives you continuous spectra. Now we are positioned on a fourth sample, which is also thin gold evaporated on the carbon backing. The purpose of this exercise is also to measure the total concentration of the gold. Now we can start with measurement. Put the spectra name and start. Immediately in the spectra, you can see the peak, which belongs to the, by kinematics, to the peak of the gold. You can see since it is the peak, it's very thin. And this continuous spectra belongs to the thick carbon backing, which this continuous spectra can be also used for the charge normalization in the analysis if you don't calibrate, for example, the solid angle using the standard. We now move to the last sample, which is indium and chromium evaporated on the silicon in order that first is deposited chromium and the second is deposited indium. We need to calculate the total amount of the both elements. Starting the measurement. So you can immediately see this spectra here on the monitor. And we can recognize two peaks, one on the heavier energy, one on the a little bit lower energy. This on the heavier energy belongs to the heavier element, which is indium. And this on the lower energy corresponds to the chromium. So these are the peaks, which means that these two films are very thin. And from this continuous spectra here, you can see this is actually the silicon backing, and you can see since it's continuous spectra that it's very thick.
For the performance of the elastic recoil detection analysis experiment, the ions used are typically heavier ions such as iodine, accelerated in the large accelerator to large energies above 20 mega electron volts. Today, we will be using the negative sputtering ion source, which produces negative iodine ions, which are later injected into the tandem accelerator. we will be using the tandem Van de Graaff accelerator with a terminal voltage of 4 megavolts. Inside the accelerator, there are many charge states produced. Of those, we will choose the +4 charge state, which in the end will give us a beam energy of 20 mega electron volts.
Now, I will demonstrate you elastic recoil detection analysis, ERD. Contrary to the radar for backscattering, where you detect only backscattered particles from the primary ion beam, here, in elastic recoil detection analysis, you detect forward scattered particles from the primary ion beam and also recoiled particles which are inside of the target. The beam is coming from the accelerator, and for ERD, we are usually using heavy ion beam like iodine of energy of tens of MeV. Target is placed inside of the chamber, and the beam recoils out the ions from the target, which are entering inside of the ERD spectrometer. This is a special type of elastic recoil detection analysis system because it consists of the two types of detectors. We have time of flight detector to measure time of flight, and we have energy detector to measure the energy of detected particles. Those two signals are measured in coincidence. Why we need time of flight beside the energy detector? Because you cannot separate two particles, different masses with the same energy using only energy detector. That's why we are using time of flight measurement, and we are doing by measuring time of flight between 2 points, this one T1 point and this T2 point. They are separated approximately by ½ meter. This time of flight signal is measured in coincidence with the energy signal collected from this detector, and this is a gas ionization chamber. It's not a silicon detector, and we are using it because it has much better energy resolution comparing to the standard silicon detector. For today's experiment, we will use 23 MeV iodine beam, which is coming under 20 degrees towards the sample surface, and time of flight ERD detector positioned at 37.5 degrees respect to the beam direction. Now I will put the first sample in the measuring position using the XYZ translator and rotation. So I'm entering the vertical value and the angle, and now the manipulator lowers down the sample at the position and rotates towards the beam. In this experiment, we will use incidence angle of 20 degrees towards the sample surface. The first ERD spectra we are showing is the spectra of the implanted standard, implanted arsenic and argon inside of the silicon. This is the same sample which we measured with radar for backscattering. You can see how the time of flight ERD spectra looks like. You have measured energy, which we plot on the y-axis, and you have measured time of flight, which we plot on the x-axis. These two signals are collected in a coincidence. This generates this kind of plot, and each of these lines presented in the plot belongs to the different element. We can start with the lightest, this is the hydrogen, then we can have the line of carbon, oxygen, this is the very continuous line, which means that this is a very thick sample, and this is the silicon, and we have line of implanted argon and line of the implanted arsenic. This line here is coming from the forward scattered primary ion beam. So the analysis goes in this way, that we, for example, select one of the elements. I will select now the arsenic, and you project either or the y-axis, which is energy detector, or the x-axis, which is the time of flight detector. And I will use time of flight because it has better energy resolution. And when you project, you can get this nice implanted peak of the arsenic, and you can do offline analysis later on. Just one more time, if we go back to this time of flight ERD spectra, you can see that contrary to the RBS, where you could saw only arsenic, argon, and silicon, we can also see the light elements presented in the sample. And this is the hydrogen, carbon, and oxygen. And I can immediately tell you that these three elements are contaminants presented at the surface because they are very thin. Now we move to the second sample, which is a thin layer of gold evaporated on the silicon dioxide. This is the same sample which we also analyzed using radar for backscattering. So you can see immediately what is present inside of the sample. So besides of the evaporated gold and silicon and oxygen, which is coming from silicon dioxide, we can see that we have contamination of the carbon at the surface and also contamination of the hydrogen at the surface. This peak here is actually forward scattering iodine on the gold, which can be also used for the analysis because it has higher statistics. Or if we are interested only in the recoils of the gold, again, we can select them and project on the, for example, time axis, and then you can get the thin peak of the gold, and this can be analyzed using standard software packages. This is the third and the last sample analyzed by time-of-flight ERD. It is a thin layer of the gold evaporated on the carbon. Here is the time-of-flight ERD spectra, energy and time-of-flight in coincidence. And from this 2D map, you can see that there is a present gold, of course. We have carbon coming from the thick backing, and we have contamination of the hydrogen and oxygen inside of the gold layer. So this is the advantage of ERD, because you can see these very low concentrations on the elements, which are actually contaminations inside of the during the evaporation process. Besides these contaminations, you can also see here that there is a very thin line of the nitrogen, which is coming from carbon backing, which means that the carbon is also contaminated with nitrogen, probably during the manufacturing process. What is the great advantage of time-of-flight ERD over the other IBA techniques? Because here we don't need the charge normalization or solid angle normalization, because we see all the elements presented in the sample. Because as you see, you can see from hydrogen to the very gold. So for the analysis and concentration normalization, we are using 100% normalization to the total elements presented in the sample. In this video, we demonstrated how RBS and ERD can be used for the thin film analysis and thin film depth profiling.
Thank you for your attention.